Hello there, and welcome to Sleep Science, where science becomes a gentle journey into dreams and the impossible feels quietly possible. Tonight, we're wandering into one of humanity's most persistent fantasies, time travel. The idea of stepping backwards to witness dinosaurs or forwards to glimpse flying cars and cities among the stars. Before we begin our journey through past and future, feel free to share what time it is and where you're listening from. Quite fitting, really, since we're about to explore whether time itself might be more flexible than we imagine. Time travel has captured our hearts for centuries, dancing through novels and films, sparking late-night conversations and childhood daydreams. But tonight, we're asking a different question. Not whether we should travel through time, but whether we could. What does science actually say about slipping between moments, rewinding yesterday, or fast-forwarding to tomorrow? We'll drift through Einstein's curved space-time, where time bends like warm honey. We'll peer into wormholes that might tunnel between decades, examine paradoxes that twist logic into knots, and discover that, in the strangest way possible, we're all time travelers already. So settle in, close your eyes if you like, and let's take a slow, dreamy wander through the science of time travel. Every bedtime story begins the same way. Once upon a time, 3 gentle words that open a door to anywhere, anywhen. Once upon a time, there were dragons. Once upon a time, there were kingdoms under the sea. Once upon a time, someone figured out how to step backwards through the hours and visit yesterday for tea. That last one hasn't happened yet, but it hasn't stopped us from dreaming about it. Time travel is humanity's most persistent fantasy, a wish so universal it appears in every culture, every generation, every imagination that's ever wondered. What if? What if we could warn Julius Caesar about the Ides of March? What if we could peek at next week's lottery numbers? What if we could go back and have that conversation we never had, or forward to meet the people we'll never know? But before we can ask whether time travel is scientifically possible, we should probably agree on what we mean by it. At its simplest, time travel is the ability to move between different points in time, just as we move between different points in space. You can walk from your kitchen to your garden. Time travel would be like walking from Tuesday to Thursday, or from 2025 to 18447. Simple concept, wildly complicated execution. There are really 2 flavors of time travel, and they taste very different. Forward time travel is moving toward the future faster than the usual 1 second per second pace. Backward time travel is the tricky one, rewinding to the past, stepping into yesterday, meeting your younger self at the coffee shop. Both have appeared in stories for centuries, but only one has any real scientific backing. Spoiler alert. It's not the one that lets you fix that embarrassing thing you said in high school. The idea of time travel has ancient roots. Hindu and Buddhist texts speak of beings who experience time differently, living through cosmic cycles that span millions of human years. Celtic folklore tells of mortals who visit fairy realms and return to find centuries have passed in what felt like hours. The Japanese legend of Urashima Taro describes a fisherman who visits an underwater palace and comes back to discover that decades have flowed by like water. These stories share a common thread. Time is not as rigid as it appears. It can stretch, compress, and surprise us. In literature, time travel really took off in the 19th century, with H.G. Wells's The Time Machine, published in 1895. Wells gave us the first mechanical time machine, a contraption that could carry its passenger forward or backward through time like a bicycle through space. Mark Twain sent his Connecticut Yankee back to King Arthur's court. Charles Dickens, while not writing time travel per se, showed us how the past could visit the present in A Christmas Carol, as Scrooge tours his timeline with ghostly guides. The 20th century brought time travel into the modern age with stories that grappled with consequences and paradoxes. Ray Bradbury's A Sound of Thunder showed how stepping on a butterfly in the past could reshape the future. Science fiction television and film made time travel a regular visitor to popular culture, from Doctor Who to Back to the Future, to countless stories where time machines look like phone booths, cars, or mysterious blue boxes. But here's what's interesting. Almost every culture that dreams up time travel also worries about it. We're drawn to the idea and simultaneously terrified of it. Why? Perhaps because time travel represents ultimate power and ultimate responsibility. The ability to change the past or know the future would make us gods, and humans have a mixed track record with power. There's also something deeply comforting about the fantasy. Time travel suggests that our mistakes aren't permanent, that regret has an expiration date, that the future holds answers to today's questions. It offers the possibility of second chances, do-overs, the chance to whisper warnings to our past selves or receive encouragement from our future ones. When scientists talk about time travel, they usually mean something more specific than literary adventures. They're asking whether the laws of physics permit objects to follow paths through space-time that loop back to earlier times. Whether you can draw a line on the map of reality that curves back to where it started, but when it started. Whether the universe has any built-in prohibition against temporal tourism. This is where things get fascinating and strange. Because while backward time travel remains highly speculative, forward time travel is not only possible, it's happening right now. Every time you move, you're traveling slightly into everyone else's future. Every time you experience gravity, time is moving a tiny bit slower for you than for someone floating in deep space. These effects are usually so small, they're negligible, but they're real, and they hint at a universe far more flexible than our everyday experience suggests. So when we ask, is time travel scientifically possible? We're really asking several questions. Can we speed up our journey into the future? Almost certainly. Can we slow down time's passage relative to others? Absolutely. Can we reverse course and visit the past? That's where science gets quiet, thoughtful, and begins to whisper about paradoxes, impossible energies, and the strange protective mechanisms the universe seems to have installed around yesterday. The truth is, time travel isn't just a science fiction fantasy or a physicist's thought experiment. It's a window into the deepest questions about reality. What is time? How does causality work? Are the past and future as real as the present? Can effects come before causes? These questions don't just matter for building time machines. They matter for understanding the universe itself. And so, we begin our gentle journey through the science of time travel, not because we're necessarily planning to build a time machine in the garage, but because asking whether it's possible helps us understand the remarkable, mysterious nature of time itself. Close your eyes, if you like, and let's wander forward through the discoveries that make the impossible seem just a little less impossible. Albert Einstein had a habit of making the impossible seem inevitable. In 1905, when he was just a young patent clerk in Switzerland, probably wondering if he'd ever amount to anything, he casually rewrote the rules of the universe. His theory of special relativity didn't just change physics. It handed humanity its first real, honest-to-goodness time travel manual. The catch? It only worked in one direction. Einstein's insight began with a simple observation about light. No matter how fast you move toward or away from a beam of light, it always travels at the same speed, about 300 million meters per second. This seems impossible at first glance. If you're driving toward an oncoming car, it approaches you faster than if you were standing still. But light doesn't work that way. Whether you're racing toward a flashlight or running away from it, the light reaches you at exactly the same cosmic speed limit. This strange fact led Einstein to a remarkable conclusion. If the speed of light is constant, then something else must be flexible. And that something else, it turns out, is time itself. Take two friends, Alice and Bob. Alice stays home, reading books and tending her garden. Bob, feeling adventurous, hops aboard a spaceship and zooms away at nearly the speed of light. To Alice, watching from Earth, Bob's clocks appear to slow down. His movements look sluggish, his aging process crawls, even his thoughts seem to unfold in slow motion. But here's the beautiful, bewildering part. Bob doesn't feel any different. From his perspective, his clocks tick normally, his coffee cools at the usual pace, and Alice, far behind on Earth, appears to be moving in slow motion. This is time dilation, and it's not science fiction. It's been measured, tested, and confirmed countless times. Particles accelerated to high speeds in laboratories live longer than they should, their internal clocks slowed by velocity. Atomic clocks flown on airplanes tick slightly slower than identical clocks left on the ground. Even the GPS satellites orbiting overhead experience time differently than we do, and their navigation systems must account for this cosmic quirk. The faster you move, the more dramatic the effect becomes. At 90% the speed of light, time passes about half as fast for you as for someone standing still. At 99% light speed, time slows to about 1/7 its normal pace. At 99.9% is roughly 1/22. The mathematics is precise, elegant, and utterly unforgiving. This creates what scientists call the twin paradox, though it's not really a paradox, just a deeply strange consequence of living in Einstein's universe. Consider identical twins, Sarah and Emma. Sarah stays on Earth, while Emma embarks on a journey to a nearby star at 99% the speed of light. The round trip takes Sarah 20 years of Earth time, but Emma, traveling at near light speed, experiences only about 2 years. When Emma returns, she's 18 years younger than her Earth-bound sister. Not metaphorically, not approximately, but literally. Her cells have divided fewer times, her hair has grown less, her memories span a shorter subjective period. She has traveled into Sarah's future. But Einstein wasn't finished reshaping reality. 10 years later, he unveiled general relativity, which revealed that gravity too can stretch and compress time. Imagine space-time as a soft mattress and massive objects as bowling balls placed on its surface. The heavier the ball, the deeper the depression it creates. What we call gravity is simply objects rolling along these curves in space-time. But here's the remarkable part. Time runs slower in the deeper parts of these gravitational wells. The stronger the gravity you experience, the slower your clocks tick relative to someone in weaker gravity. On Earth, this effect is tiny but measurable. Your head, being slightly farther from Earth's center than your feet, ages infinitesimally faster. Atomic clocks placed at different altitudes show this difference clearly. Near more massive objects, the effect becomes dramatic. Close to a black hole, where gravity is so strong that not even light can escape, time dilation becomes extreme. An astronaut orbiting near a black hole's event horizon might experience minutes while years pass for observers safely distant. In fact, if you could somehow survive a close approach to a black hole, you could use it as a time machine, emerging into the far future of the universe. This isn't theoretical anymore. We see gravitational time dilation in action every day. The GPS satellites orbiting Earth are moving fast enough and sitting high enough in Earth's gravitational field that their onboard clocks tick about 38 microseconds per day, faster than clocks on the surface. Without constant correction for this relativistic effect, your phone's GPS would be off by several kilometers within hours. Einstein's theory doesn't just describe exotic physics. It helps you find the nearest coffee shop. So here's the quietly astonishing truth. Forward time travel isn't just possible, it's unavoidable. Every moment of your life, you're traveling into the future at 1 second per second. But by moving fast or experiencing strong gravity, you can slow that journey, allowing the rest of the universe to race ahead into tomorrow while you take your time getting there. The universe seems to have a sense of humor about this. It allows us to speed into the future, but remains frustratingly silent about returning to the past. Einstein's equations do contain some solutions that might permit backward time travel. Closed time-like curves, they're called, but they require such exotic conditions that most physicists suspect the universe has built-in safeguards against temporal tourism to yesterday. Still, the fact that we can travel forward through time, that Einstein's theories turn science fiction into science fact, hints at a universe far stranger and more flexible than our everyday experience suggests. Time isn't the rigid, universal backdrop Newton imagined. It's a flowing, bending, personal thing, as individual as your heartbeat and as cosmic as the dance of galaxies. And perhaps that's enough magic for now. The universe hands us forward time travel as a gift, a reminder that reality is far more wonderful than common sense suggests. Not bad for a Peyton Clark who once worried he might not amount to much. Imagine space-time as a vast cosmic apple, and someone just handed you a very small worm. Now, if that worm wanted to travel from one side of the apple to the other, it could crawl along the surface, following the long, curved path around the apple's skin. Or, being a clever worm with a taste for shortcuts, it could simply tunnel straight through the core, emerging on the far side, having traveled a much shorter distance. This charming analogy captures the basic idea behind wormholes, theoretical tunnels through space-time that could connect distant regions of the universe, or even different times. They're called Einstein-Rosen bridges in the physics literature, named after Albert Einstein and Nathan Rosen, who first described them mathematically in 1935. But wormhole is much more fun to say, and it paints exactly the right picture of space-time with holes bored through it. The mathematics behind wormholes emerges naturally from Einstein's general relativity. When you solve Einstein's equations under certain conditions, you get solutions that describe passages connecting different regions of space-time. Picture a folded piece of paper with a tunnel connecting the two layers. If space-time can be folded and connected in similar ways, then wormholes represent the ultimate cosmic shortcuts, But here's where reality starts getting complicated, which is often the case when dealing with the universe's more exotic possibilities. Just because the mathematics allows for wormholes doesn't mean they can actually exist, much less that you could use one to pop over to last Tuesday for a quick visit. The first problem is stability. Most of the wormhole solutions that emerge from Einstein's equations are catastrophically unstable. They pinch closed faster than light can travel through them, making them useless for travel and rather dangerous for anything that might be caught inside when they collapse. It's like trying to crawl through a tunnel that's actively caving in. Even if you could enter one end, you'd be crushed long before reaching the other side. To keep a wormhole open long enough for something to pass through, you'd need what physicists call exotic matter, stuff with negative energy density. This isn't just regular matter running in reverse. It's something that would have genuinely bizarre properties, like negative pressure and the ability to push space-time apart rather than pull it together. We're not even sure such matter can exist, and if it can, we certainly don't know how to make it. The energy requirements are equally staggering. To create and maintain a wormhole large enough for a person to travel through, you'd need exotic matter with negative energy equivalent to the mass energy of an entire star. That's not the kind of thing you can whip up in a laboratory, or even with the combined efforts of an entire civilization. It's more along the lines of rearrange the local galaxy levels of energy. And then there's the question of where a wormhole would lead. Even if you could create one, you can't exactly program it like a cosmic GPS. The other end might open up in the vacuum of intergalactic space, inside a star, or in a region of space-time so distant that the universe would end long before you could reach anything interesting. It's like digging a tunnel without knowing where you'll emerge. You might pop up in your neighbor's garden, or you might find yourself in the middle of the ocean. But suppose for a moment that these problems could be solved. Imagine some advanced civilization figures out how to create stable, traversable wormholes. Could they be used for time travel? Here's where things get deliciously strange. A wormhole that initially connects 2 points in space at the same time could, in principle, be turned into a time machine. Here's one scenario. Imagine you create a wormhole that connects your laboratory to a point in space a light year away. Then you take one end of the wormhole, call it the exit, and accelerate it to near light speed, taking advantage of time dilation. Due to Einstein's relativity, time passes more slowly for the moving exit than for the stationary entrance. After accelerating the exit for a while, you bring it back to your laboratory. Now you have something remarkable, a wormhole where the entrance and exit are in the same place. But the exit is in the past relative to the entrance. Step through the entrance, and you emerge from the exit at an earlier time. Voila, a time machine. The mathematics of this scenario seems to work, which has led to some fascinating theoretical discussions among physicists. But the universe, being somewhat protective of causality, might have other ideas. Some scientists propose that quantum effects would destroy any wormhole the moment it became a time machine, filling it with destructive radiation feedback loops. It's as if the universe has a built-in immune system against temporal paradoxes. Stephen Hawking, never one to shy away from profound questions, proposed what he called the chronology protection conjecture, the idea that the laws of physics somehow prevent the formation of closed time-like curves, the technical term for paths through space-time that loop back to earlier times. The universe, in this view, actively prevents time machines from forming, though Hawking admitted he didn't know exactly how. Still, wormholes remain a fascinating theoretical possibility, sitting at the intersection of extremely advanced physics and wild speculation. They appear regularly in solutions to Einstein's equations, hint at deep connections between quantum mechanics and gravity, and offer tantalizing possibilities for faster-than-light travel and time manipulation. Some physicists have even suggested that quantum entanglement, the spooky connection between particles that Einstein called spooky action at a distance, might actually work through microscopic wormholes. In this view, entangled particles are connected by tiny tunnels through space-time, making the quantum world a foam of miniature wormholes too small to travel through, but large enough to carry information instantaneously across vast distances. Others have proposed that black holes might be connected by wormholes, with matter falling into one black hole potentially emerging from another, somewhere else in space and time. These ideas remain highly speculative, but they hint at a universe far more interconnected than we might imagine. For now, wormholes remain beautiful mathematical objects, theoretical tunnels through space-time that capture our imagination and challenge our understanding of reality. They exist in equations and thought experiments, in science fiction stories and late-night discussions about the nature of time and space. Whether they exist in reality, and whether we could ever use them for travel through space or time, remains an open question. But perhaps that's part of their charm. Wormholes represent the universe at its most mysterious and generous, offering possibilities so strange and wonderful that they stretch our understanding to its limits. They remind us that reality might be far more exotic than our everyday experience suggests, and that the cosmos still holds secrets we're only beginning to glimpse. Time travel comes with a peculiar problem. What happens when the impossible meets the inevitable? The moment you start seriously considering backward time travel, you run headfirst into paradoxes that twist logic into knots and make philosophers reach for stronger tea. The most famous of these puzzles is the grandfather paradox, which goes something like this. Suppose you build a time machine and travel back to 1925. While there, you accidentally prevent your grandfather from meeting your grandmother. Perhaps you bump into him at the crucial moment, or give him directions to the wrong dance hall, or simply distract him with conversation about the future of aviation. Without their meeting, your parent is never born. Without your parent, you're never born. But if you're never born, who traveled back in time to prevent the meeting in the first place? It's the kind of logical loop that makes your brain feel like it's trying to untie a knot made of smoke. The paradox doesn't require anything as dramatic as harming your grandfather. Any change that prevents your own existence creates the same impossible situation. You could prevent your parents from meeting, cause your great-grandmother to move to a different city, or simply introduce a butterfly effect that cascades through history until your timeline never comes to pass. But the grandfather paradox is just the beginning. The bootstrap paradox poses an even stranger question. Where do things come from in a universe that allows time loops? Imagine you travel back in time and give Shakespeare a complete collection of his plays, which he then publishes as his own work. Years later, you read those same plays, memorize them, and eventually travel back to give them to Shakespeare. So who really wrote Hamlet? Shakespeare got it from you, but you got it from Shakespeare. The information exists in a closed loop with no discernible origin, like a cosmic case of spontaneous literature. Another puzzle emerges with predestination, the idea that attempts to change the past might actually cause the events you're trying to prevent. You travel back to warn Julius Caesar about the Ides of March, but your warning makes him suspicious of his advisors, leading him to behave erratically, which convinces the conspirators that he must be stopped immediately. Your attempt to save Caesar actually ensures his assassination. The future, it seems, has a way of protecting itself. These paradoxes have sparked decades of creative solutions, each stranger than the last. One approach is the self-consistency principle, proposed by physicist Igor Novikov. This idea suggests that the universe somehow arranges events so that time travel never creates paradoxes. If you try to prevent your grandfather from meeting your grandmother, something will always stop you. You'll slip on a banana peel at the crucial moment, or suddenly develop laryngitis, or be distracted by an unexpected rainstorm. The universe becomes a cosmic conspiracy to preserve its own logical consistency. Another solution is the many worlds interpretation, borrowed from quantum mechanics. In this view, traveling to the past doesn't change your original timeline. It creates a new one. When you prevent your grandfather from meeting your grandmother, you create an alternate universe where you're never born. But your original timeline continues to exist, with a slightly confused grandfather wondering what happened to that strange visitor who kept asking about dance halls. You're not stuck in a paradox. You're simply stranded in the wrong universe. Some physicists propose the Novikov self-consistency conjecture, which goes beyond just preventing paradoxes to suggest that the laws of physics actively enforce logical consistency. In this view, if you tried to shoot your grandfather, quantum effects would conspire to make your gun jam, or alter the trajectory of the bullet, or cause you to miss in some other improbable but not impossible way. The universe becomes deterministic in a very strange sense, not because events are predetermined, but because logical consistency retroactively determines what must have happened. There's also the timeline protection hypothesis, which suggests that small changes to the past are absorbed by the natural resilience of history. Kill a butterfly in the Cretaceous period, and evolution finds another path. Prevent a minor historical figure from being born, and someone else steps up to fill their role. Major historical events have a kind of gravitational pull that draws history back toward the same general outcomes, even when details change. But perhaps the most elegant solution is also the most sobering. Maybe backward time travel is simply impossible, and the paradoxes exist to show us why. In this view, the universe doesn't need elaborate mechanisms to prevent paradoxes because it never allows the conditions that would create them. The laws of physics might contain a built-in chronology protection system that prevents time machines from ever forming, or destroys them the moment they attempt to access the past. Stephen Hawking was fond of this idea, though he admitted he couldn't prove it. He once said that the best evidence against time travel was that we hadn't been invaded by tourists from the future. After all, if time travel were ever invented, wouldn't some future civilization use it to visit the past? The absence of temporal tourists might be the universe's way of telling us that backward time travel remains forever out of reach. Some researchers have proposed more exotic solutions involving quantum mechanics. In the quantum world, particles can exist in multiple states simultaneously until observed. Perhaps time travelers exist in the superposition of having and not having changed the past, collapsing into the version that preserves consistency only when observed. Or maybe consciousness itself plays a role, with awareness acting as the mechanism that selects which timeline becomes real. The more you dig into temporal paradoxes, the more they reveal about our assumptions regarding time, causality, and free will. They force us to ask fundamental questions. Is the past fixed or changeable? Does the future already exist, waiting for us to arrive? Can effects come before causes? Are we the authors of our actions or characters in a story that's already been written? These questions matter even if we never build a time machine. They illuminate the nature of causality, the relationship between knowledge and determinism, and the strange loops that emerge when intelligence becomes sophisticated enough to contemplate its own existence. In a sense, we're all caught in temporal paradoxes already, using our knowledge of the past to shape our future, which then becomes the past that shapes someone else's future. Perhaps the real purpose of temporal paradoxes isn't to show us how to build time machines, but to reveal the elegant, mysterious, and sometimes impossible logic that underlies reality itself. They're puzzles wrapped in thought experiments, designed to stretch our minds and remind us that the universe is under no obligation to make sense in ways we find comfortable. And maybe that's enough. Maybe the beauty of temporal paradoxes lies not in solving them, but in appreciating the depths they reveal, the strange loops and logical knots that exist at the very foundations of time, causality, and existence itself. If Einstein thought time was weird, quantum mechanics said, "Hold my particles." The quantum world, that mysterious realm of atoms and subatomic particles, follows rules so strange that even physicists sometimes wonder if the universe is playing an elaborate joke on anyone trying to understand it. And when it comes to time, quantum mechanics doesn't just bend the rules. It seems to rewrite them entirely. In the everyday world, time feels like a one-way street. Eggs break, coffee cools, memories fade, and entropy increases with the steady march of seconds. But zoom down to the quantum level, and time becomes something far more mysterious and flexible. Particles can tunnel through barriers they shouldn't be able to cross, exist in multiple states simultaneously, and seem to influence each other instantly across vast distances. Some of these quantum quirks hint at possibilities for time travel that classical physics never imagined. Let's start with quantum tunneling, one of the most elegant tricks in the quantum playbook. Imagine rolling a ball toward a hill that's too high for the ball to climb over. In the classical world, the ball would simply roll back. But in the quantum world, there's a small probability that the ball could simply appear on the other side of the hill, having tunneled through the barrier. This isn't science fiction. It's happening right now in the electrons flowing through your computer, the fusion reactions powering the sun, and countless other quantum processes. Now here's where it gets interesting for time travel. Some interpretations of quantum tunneling suggest that particles don't just tunnel through space, but through time as well. The mathematics hint that during the tunneling process, particles might spend negative time crossing the barrier, arriving at the other side before they technically should, given the speed of light. It's as if they take a shortcut, not just through space, but through time itself. This has led some physicists to propose that quantum tunneling might allow for microscopic time travel. Particles could tunnel backward through time, arriving at their destination slightly before they left. The effect would be tiny. We're talking about time intervals shorter than the time it takes light to cross an atomic nucleus, but it would still represent genuine backward time travel. But quantum mechanics offers even stranger possibilities. Consider the many worlds interpretation proposed by physicist Hugh Everett III. In this view, Every quantum measurement causes the universe to split into multiple parallel realities, each representing a different possible outcome. When you observe a quantum particle that could be spinning up or down, the universe divides. In one branch, you see spin up. In another, you see spin down. Both versions of you continue to exist, unaware of each other. If many worlds is correct, then time travel might not create paradoxes. It might create parallel timelines. Travel back to prevent your grandfather from meeting your grandmother, and you don't erase your own existence. You simply move to a timeline where you were never born. Your original timeline continues without you, while you're stuck in a new one where everything is subtly different. It's not quite the time travel of science fiction, but it suggests that the universe might have built-in protection against temporal paradoxes. Quantum entanglement adds another layer of strangeness to the temporal puzzle. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, and suspected it violated the speed of light limit. But experiments have confirmed that entanglement is real, and some interpretations suggest it might work through connections that exist outside normal space-time. This has led to wild speculation about quantum time travel. If entangled particles can influence each other instantaneously across space, perhaps they can influence each other across time as well. Some researchers have proposed that information could be sent backward through time using quantum entanglement, though the details remain highly theoretical and controversial. There's also the intriguing possibility of closed time-like curves in quantum mechanics. Unlike the large-scale closed time-like curves that might emerge from wormholes or cosmic strings, quantum closed time-like curves would exist at the subatomic level. Particles could follow paths through space-time that loop back to their own past, creating quantum time loops. Remarkably, the mathematics suggests that quantum systems might naturally resolve the paradoxes that plague classical time travel. When a quantum particle travels back in time and encounters its past self, instead of creating a logical contradiction, the two states might simply interfere with each other, like waves in a pond. The result would be a self-consistent solution, where the particle's time-traveling adventure was always part of its history. Some physicists have even proposed that quantum effects might allow for the existence of quantum time machines, devices that use quantum mechanical principles to send information, if not matter, backward through time. These hypothetical machines would exploit the strange properties of quantum superposition and entanglement to create informational loops that extend into the past. But perhaps the most mind-bending quantum approach to time travel involves the nature of measurement itself. In quantum mechanics, the act of observation plays a crucial role in determining reality. Some interpretations suggest that consciousness, or at least the act of measurement, helps collapse quantum superpositions into definite states. This has led to exotic theories where time travel might be possible through quantum consciousness effects, where the mind could somehow access past or future quantum states. The quantum Zeno effect offers another curious twist. Named after the ancient Greek philosopher who proposed paradoxes about motion and time, this effect occurs when frequent observations of a quantum system prevent it from evolving. Watch a quantum particle closely enough, and you can literally freeze its evolution in time. Some researchers wonder if this could be exploited for temporal manipulation, creating regions where time flows differently or even backwards. Of course, most of these ideas remain highly speculative. The quantum world is notoriously difficult to scale up to human-sized objects and experiences. Quantum effects tend to be incredibly fragile, destroyed by the slightest interaction with the environment. A quantum time machine might work for individual particles, but fail completely when you try to send anything larger than an atom through time. Still, quantum mechanics continues to surprise us. The field that began with Max Planck's study of black-body radiation has revealed a universe where particles can be in multiple places simultaneously, where the future can influence the past through retrocausality, and where information might travel faster than light through the mysterious channels of entanglement. Each new quantum discovery seems to push the boundaries of what's possible, suggesting that reality is far stranger and more flexible than our everyday experience indicates. If backward time travel is ever achieved, it might not be through the massive engineering projects of wormholes and cosmic strings, but through the delicate, precise manipulation of quantum states. For now, quantum time travel remains a beautiful theoretical possibility, dancing at the edges of our understanding like particles at the edges of a measurement. But in a universe where observation changes reality and particles tunnel through impossible barriers, perhaps even the impossible deserves a second look. Right now, as you listen to these words, you're traveling through time at exactly 1 second per second. It's the most natural thing in the universe, so ordinary that we rarely think about it. But here's something quietly remarkable. You're not just passively experiencing time, you're actively traveling through it, and not everyone's journey unfolds at quite the same pace. The universe, it turns out, is already a time machine. Einstein's revelations about relativity didn't just give us theoretical possibilities for exotic time travel. They revealed that we're all time travelers already, surfing through space-time at slightly different rates, depending on how fast we move and how deep we sit in gravity's gentle embrace. Consider your morning commute. If you drive to work at highway speeds, you're traveling fractionally slower through time than someone walking. The difference is absurdly small. We're talking about nanoseconds over the course of a lifetime, but it's real and measurable. Your car essentially becomes a tiny time machine, carrying you slightly into everyone else's future. The faster you go, the more pronounced the effect becomes, though you'd need to approach the speed of light before you'd notice anything dramatic. Commercial airline pilots experience this time travel effect more noticeably. Flying at 500 miles per hour for years of their career, they age slightly less than their ground-bound counterparts. It's not enough to keep them looking young for their retirement party, but atomic clocks have confirmed the effect. By the time a pilot retires, they've gained perhaps a few microseconds on the rest of us. Not exactly youth serum, but genuine time travel nonetheless. The astronauts aboard the International Space Station take this to another level. Orbiting Earth at about 17,500 miles per hour, they experience time dilation from their high speed, but they're also farther from Earth's center, experiencing weaker gravity, which makes their time run slightly faster. These two effects partially cancel each other out, but the speed effect wins. Astronauts age about 0.01 seconds less for every year they spend in orbit. Russian cosmonaut Sergei Krikalev, who spent a total of about 803 days in space, has traveled about 0.02 seconds into the future compared to the rest of us. He holds the current record for human time travel. But the most dramatic everyday example of time travel happens in your pocket. GPS satellites orbit Earth at about 12,550 miles per hour and at an altitude of roughly 12,550 miles. At this speed and distance from Earth's gravity, their onboard atomic clocks tick about 38 microseconds per day, faster than identical clocks on the ground. That might not sound like much, but GPS works by measuring the time it takes signals to travel from satellites to your phone. If those clocks weren't constantly corrected for relativistic effects, your location would be off by several miles within hours. Every time you use your phone's map to find a coffee shop, you're relying on time travel corrections. The satellites are literally living in the near future relative to Earth, and engineers must constantly adjust for this temporal displacement. In a very real sense, GPS is a practical time machine, one that we use billions of times every day without thinking about it. Gravity adds its own temporal wrinkles to daily life. Your head, being slightly farther from Earth's center than your feet, experiences weaker gravity and therefore ages infinitesimally faster. The difference amounts to about 90 billionths of a second over a typical 80-year lifetime. Hardly enough to worry about, but detected easily by sufficiently precise atomic clocks. Mountains experience this effect more dramatically. An atomic clock placed on top of Mount Everest would tick noticeably faster than one at sea level. The difference is only about 30 microseconds per year, but it demonstrates that altitude literally gives you a head start on time. In a very technical sense, people living in Denver age faster than people living in New Orleans, though you'd need incredibly precise instruments to measure the difference. These effects become more pronounced near massive objects. Atomic clocks have been used to detect the tiny time dilation effects of local geography. The clock runs slightly slower when placed near a large mountain because the mountain's mass creates a stronger gravitational field. Scientists have even proposed using ultra-precise atomic clocks to detect underground oil deposits or mineral veins by measuring tiny variations in time flow caused by density differences in the Earth's crust. But perhaps the most mind-bending aspect of everyday time travel is that we're all moving through time at different rates, depending on our motion through space. Earth orbits the Sun at about 67,000 miles per hour. The solar system moves through the galaxy at roughly 514,000 miles per hour. The Milky Way galaxy is racing through space at about 1.3 million miles per hour, relative to the cosmic microwave background. All of this motion affects the rate at which we experience time, though the effects are tiny and essentially identical for everyone on Earth. The time dilation effects in our daily lives are minuscule, but they add up in interesting ways. If you live in a city with tall buildings and spend time in elevators, you're constantly experiencing tiny shifts in time flow as you move up and down through Earth's gravitational field. If you exercise regularly, increasing your average speed through space, you age slightly slower than someone who sits still. If you live at a high altitude, you age faster than someone at sea level. These effects raise fascinating questions about the nature of time and aging. If time passes differently for different people in different circumstances, what does it mean to say we're all the same age? Your birth certificate might say you're 30 years old, but depending on your life history, how much you've traveled, what altitudes you've lived at, how fast you've moved, you might be nanoseconds younger or older than someone born at the same moment. The universe doesn't just allow time travel, it insists on it. Every step you take, every car ride, every flight, every moment spent at different altitudes or moving at different speeds, carries you through time at your own unique pace. We're all time travelers, each following our own slightly different path through space-time, aging at rates that depend on the intricate details of our motion and position. This isn't the dramatic time travel of science fiction, where heroes leap through decades in gleaming machines. It's subtler and more beautiful, a universe where time is personal, where each life follows its own temporal trajectory, where the passage of moments depends on the dance of matter and motion. We may not have time machines in our garages, but we carry them with us everywhere we go. Every heartbeat is a journey through time. Every breath a step into the future, every movement a gentle nudge against the flow of space-time itself. Building a time machine, as it turns out, requires more energy than most civilizations have lying around. The universe seems to have set the energy requirements for backward time travel somewhere between completely impossible and laughably impractical, which makes you wonder if it's trying to tell us something. Let's start with the gentler forms of time travel, the ones that merely bend time rather than breaking it entirely. To achieve significant time dilation through speed, you need to approach the speed of light. This sounds straightforward until you check the energy bill. The faster you want to go, the more energy you need, and the relationship isn't linear, it's exponential. Accelerating a single person to 90% the speed of light, where time dilation becomes dramatic, would require about 25 times the current annual energy production of our entire planet. That's to speed up one human being, not counting the mass of their spacecraft, life support systems, or snacks for the journey. Push toward 99% light speed, where time really starts crawling, and you'd need roughly 500 times Earth's annual energy output. Near 99.9% light speed, the energy requirements approach the absurd. Thousands of times our planetary energy budget, just to make one person's watch tick slowly. And here's the cruel joke. As you approach the speed of light, your mass effectively becomes infinite, requiring infinite energy to accelerate further. The universe has installed a cosmic speed limit with an infinitely expensive toll booth. But speed-based time travel looks positively economical compared to the other options. Want to create a traversable wormhole? You'll need what physicists call exotic matter, material with negative energy density that can hold open the throat of the wormhole and prevent it from collapsing. The amount of exotic matter required to keep a human-sized wormhole stable has been estimated at roughly the mass energy equivalent of the planet Jupiter, with a negative sign in front of it. That's not just a lot of energy, it's a lot of energy that may not exist. Negative energy density isn't something you can mine or manufacture in any conventional sense. It's more like anti-energy, energy running backwards, energy that pushes space-time apart instead of pulling it together. We have some theoretical hints that quantum effects might create tiny amounts of negative energy in certain circumstances, but scaling that up to Jupiter mass quantities is like trying to power a city with the static electricity from rubbing balloons on your hair. Closed time-like curves present their own energy challenges. Whether created through rotating black holes, cosmic strings, or other exotic mechanisms, they typically require masses and energies that dwarf anything available to a single planet or even a single star system. Creating a stable time loop large enough and persistent enough for human travel might require manipulating objects with the mass of multiple stars, or engineering on scales that encompass entire solar systems. Some of the more exotic time travel proposals push energy requirements into the realm of the cosmically ridiculous. Alcubierre's warp drive, which could theoretically allow faster than light travel, and thus time travel, originally required more energy than exists in the observable universe. Later refinements have brought this down to merely the mass energy of several planets, which represents progress of sorts, though not the kind that would get you funding from venture capitalists. The grandfather paradox may have its own energy cost. Some theoretical frameworks suggest that the universe might allow time travel, but extract an enormous energy penalty for any changes to the timeline. In this view, traveling to the past might be possible, but altering events would require energy proportional to the magnitude of the change. Preventing a major historical event might cost more energy than a civilization could generate in centuries. Then there's the quantum approach to time travel, which presents different but equally daunting challenges. Quantum time machines would likely require maintaining quantum coherence across macroscopic scales and time periods, keeping quantum states stable while they loop through time. This is extraordinarily difficult because quantum coherence is fragile. The slightest interaction with the environment can destroy quantum states, and the larger and longer lasting you want your quantum time loop to be, the more energy you need to shield it from decoherence. Some physicists have calculated that a quantum time machine capable of sending even a single bit of information backward in time might require energy equivalent to the mass of a small asteroid, all focused into a quantum system delicate enough to be disrupted by stray photons. It's like trying to build a house of cards inside a hurricane using cards made of soap bubbles. The energy problems extend beyond creation to maintenance. Even if you could somehow gather the energy to create a time machine, keeping it running would present ongoing challenges. Wormholes want to collapse, exotic matter wants to decay, quantum states want to decohere. You'd need to constantly pump energy into your time machine to prevent it from becoming an expensive pile of ordinary matter scattered across space-time. There's also the efficiency problem. Most proposed time machines waste enormous amounts of energy. A wormhole time machine might require the energy output of a star to send a postcard to the past. The energy cost per unit of temporal displacement could make time travel the most expensive form of transportation ever conceived, making a taxi ride across town look like a bargain by comparison. But perhaps the most sobering aspect of the energy problem is what it suggests about the universe's attitude toward time travel. The fact that every known time travel mechanism requires exotic matter, impossible energies, or universe-scale engineering projects hints that the cosmos might have built-in protections against temporal tourism. It's as if the universe is saying, sure, you can travel through time, but first, you need to harness the energy output of entire galaxies and invent matter that may not exist. It's not technically impossible, just effectively impossible for any civilization that doesn't have a spare universe lying around for parts. Some optimists point out that our ancestors would have considered many modern technologies impossible due to their energy requirements. Flying required more energy than any horse could provide, but we invented engines. Global communication required more energy than any human could generate, but we built power plants. Perhaps time travel is simply waiting for the next breakthrough in energy generation or exotic matter manipulation. But there's a difference between the energy challenges of flight and the energy challenges of time travel. Airplanes work within the known laws of physics using known forms of matter and energy. time machines require violating or at least severely bending those laws, using materials that might not exist and energies that might not be available. The energy problem doesn't definitively rule out time travel, but it does suggest that if time machines are ever built, they'll likely be the product of civilizations so advanced that their technology would seem like magic to us. Civilizations that can manipulate matter and energy on cosmic scales, that have access to exotic forms of matter we can barely imagine, that think nothing of concentrating the energy output of stars into devices smaller than planets. Until then, we're left with the gentle time travel that surrounds us, the tiny temporal displacements of high-speed travel, the microscopic time dilation of living at altitude, the everyday miracle of moving through time at our own steady pace. Perhaps that's enough. Perhaps the universe's energy requirements for dramatic time travel are its way of ensuring that we appreciate the simple wonder of existing in the present moment, 1 second at a time. Every impossible thing was once just an idea waiting for the right equation. 100 years ago, the notion that space and time could bend and stretch seemed like fantasy. 50 years ago, quantum entanglement sounded like science fiction. Today, we navigate using satellites that account for time dilation and communicate through quantum effects that Einstein called spooky. Tomorrow's physics might make today's impossibilities look as mundane as sunrise. The frontier of time travel research today lives primarily in the realm of theoretical physics, where brilliant minds push mathematics to its limits and occasionally stumble upon solutions so strange they surprise even their creators. These theories don't promise working time machines next week, but they hint at possibilities that could reshape our understanding of time, causality, and the fundamental nature of reality. One of the most intriguing current research areas involves closed time-like curves in the context of quantum mechanics. Unlike the massive, energy-hungry closed time-like curves proposed in general relativity, quantum closed time-like curves could potentially exist at microscopic scales. Recent theoretical work suggests that quantum systems might naturally resolve temporal paradoxes through interference effects, allowing information to travel backward in time without creating logical contradictions. Researchers have even developed quantum computing models that incorporate closed time-like curves, exploring how information might behave in loops through time. These studies suggest that quantum time travel might not just be possible, but computationally useful, potentially allowing quantum computers to solve certain problems exponentially faster by accessing information from their own future calculations. Another promising direction involves the intersection of quantum mechanics and gravity, a frontier where physicists are still trying to understand how the very small and the very large connect. Some theories suggest that quantum gravity effects occurring at the Planck scale, where space and time become granular rather than smooth, might create natural pathways for temporal manipulation. Loop quantum gravity. One approach to quantum gravity suggests that space-time has a discrete structure at the smallest scales, like a cosmic foam made of tiny loops and nodes. In this view, time travel might be possible through quantum tunneling between different temporal regions of this space-time foam. While the effects would be minuscule, they might be amplified through careful engineering or quantum coherence effects. String theory, another approach to quantum gravity, offers its own temporal possibilities. In string theory's higher dimensional landscape, time travel might be possible through paths that extend beyond our familiar 3 dimensions of space and one of time. Several string theory models include additional time dimensions, suggesting that what we experience as linear time might be just one slice of a more complex temporal structure. The concept of holographic time, emerging from research into black holes and information theory, suggests that time might be an emergent property rather than a fundamental feature of reality. If time itself is holographic, encoded on some lower dimensional boundary of space-time, then manipulating that encoding might allow for temporal effects that seem impossible in our conventional view of time. Advances in metamaterials and exotic matter research might also open new possibilities. Metamaterials can already manipulate electromagnetic fields in ways that seemed impossible just decades ago, creating invisibility cloaks and optical effects that bend light around objects. Future metamaterials might be able to manipulate space-time itself, creating local regions where time flows differently or where temporal loops become possible. The search for exotic matter continues on multiple fronts. While we haven't found any material with negative energy density, researchers are exploring quantum effects that might create effective negative energy in carefully controlled circumstances. The Casimir effect, where quantum fluctuations create attractive forces between closely spaced plates, hints at the possibility of extracting negative energy from the quantum vacuum. Investigations into whether certain configurations of electromagnetic fields might create exotic matter effects are ongoing, along with studies of whether rapid motion through specially arranged magnetic fields could generate the space-time distortions needed for time travel. These approaches remain highly speculative, but they're grounded in known physics rather than purely theoretical constructs. Artificial intelligence and advanced computation might also play a role in future time travel research. AI systems could explore vast parameter spaces of physical theories, searching for combinations of conditions that might allow for time travel effects. Machine learning might identify patterns in the solutions to Einstein's equations that human physicists have overlooked, revealing new pathways to temporal manipulation. The development of room temperature superconductors, practical nuclear fusion, or other breakthrough energy technologies could make previously impossible experiments feasible. While the energy requirements for dramatic time travel remain enormous, advances in energy generation and manipulation might make smaller-scale temporal effects accessible to human technology. Precision measurement technology continues to improve at a remarkable pace. Atomic clocks now achieve accuracies that would have been unimaginable just decades ago, allowing us to detect ever smaller temporal effects. Future generations of these instruments might be sensitive enough to detect quantum temporal effects, microscopic time loops, or other subtle signatures of time travel that remain hidden with current technology. Research into consciousness and its relationship to quantum mechanics might also reveal new aspects of time travel. Some theories suggest that consciousness plays a role in collapsing quantum superpositions, and if consciousness has quantum aspects, it might interact with temporal effects in unexpected ways. While highly speculative, these ideas could lead to discoveries about the nature of time perception and subjective temporal experience. Perhaps most intriguingly, our understanding of time itself continues to evolve. Some physicists now question whether time is fundamental or emergent, whether it flows or is simply an organizing principle for change. If time is emergent from more basic physical processes, then understanding those processes might reveal new ways to manipulate temporal experience. The next century might bring developments in physics as revolutionary as quantum mechanics or relativity were in the past century. New mathematical frameworks might emerge that make time travel not just possible, but inevitable under certain conditions. Or we might discover fundamental reasons why a backward time travel must remain impossible, helping us understand the deep structure of causality and the nature of physical law. Whatever tomorrow's science reveals, it will likely surprise us. The history of physics is filled with discoveries that seemed impossible until they weren't. Technologies that appeared magical until they became mundane. Time travel might remain forever beyond our reach, or it might become as common as global communication is today. The next century might bring revelations that reshape our understanding of time, causality, and possibility itself. Each theoretical breakthrough, each new insight into temporal mechanics, expands our vision of what the universe might be capable of. Whether we ever build working time machines or not, the journey of exploration has already changed how we see reality. Perhaps the most wonderful thing about time travel isn't whether it's possible, but why we dream about it at all. In our heart of hearts, beneath all the equations and energy calculations, the wormholes and paradoxes, lies something profoundly human. The desire to step outside the river of time and see it whole. To visit the moments that shaped us. To whisper comfort to our younger selves, or glimpse the future that awaits. Time travel represents more than just exotic physics. It's a mirror that reflects our deepest relationships with memory, regret, hope, and the persistent feeling that time moves too quickly for the living of life. We dream of traveling through time because we are temporal beings in ways that go far beyond physics. We exist not just in the present moment, but across the span of memory and anticipation, carrying our past with us and reaching toward our future. Consider what we're really asking when we imagine time travel. The desire to correct mistakes, but also to experience beautiful moments again. The longing to warn our ancestors about coming dangers, while also hoping to meet them, to understand where we came from. The wish to see the future, balanced against the need to know that our present actions matter, that tomorrow remains unwritten and full of possibility. These desires reveal something beautiful about human consciousness. We are the universe's way of remembering itself, of experiencing the passage of time not just as a physical process, but as something meaningful, poignant, and profound. Our longing for time travel is really a longing for control over the story of our lives, for the ability to edit the chapters we regret and preview the endings we hope to write. But perhaps the universe's apparent prohibition against backward time travel is not a limitation, but a gift. If we could change the past, would we ever stop? Every life contains moments we wish we could revisit, words we wish we hadn't spoken, chances we wish we'd taken. The ability to edit our history might trap us in an endless cycle of revision, forever tweaking our timeline instead of living forward into possibility. The grandfather paradox, for all its logical complexity, might be existence's way of protecting something essential, the integrity of experience itself. Our mistakes and our triumphs, our losses and our discoveries, all weave together into the fabric of who we are. Pull one thread, and the entire tapestry might unravel. The impossibility of changing the past preserves the weight of our choices, the meaning of our actions, the precious irreversibility that makes each moment matter. Forward time travel, which physics readily allows, offers a different kind of poetry. It reminds us that we are all moving toward an unknown future at exactly the pace the universe intended. We cannot rush to tomorrow or skip the difficult parts of becoming who we're meant to be. But we can speed up our journey through careful motion and judicious gravity, carrying our present selves into the future like seeds planted in time. The time dilation effects that surround us in daily life, the microscopic temporal shifts of motion and altitude, the gentle warping of time by Earth's gravity, remind us that time is not the rigid backdrop we imagine, but something fluid and personal. Each of us travels through time at our own pace, shaped by the paths we choose and the places we go. In the most literal sense, no two people age identically. We each follow our own temporal trajectory through the cosmos. This personalness of time connects to something deeper about consciousness and existence. We don't just experience time, we create it through our awareness, our memory, our anticipation. The present moment exists only in the fleeting interface between memory and possibility, between what was and what might be. We are temporal artists, painting our lives across the canvas of space-time with choices that create the future and memories that preserve the past. The quantum mechanical aspects of time, the uncertainty, the multiple possibilities existing in superposition until observation collapses them into actuality, mirror something essential about human experience. We live in a quantum state of possibility until consciousness makes choices that define reality. Every decision is a kind of time travel, collapsing potential futures into actual presence. Even if we never build classical time machines with gleaming controls and spinning dials, we are already time travelers in the most important sense. We carry the past with us in memory and DNA, in habits and scars and stories passed down through generations. We reach into the future through our actions, our children, our art, our influence on the world. We exist simultaneously in multiple times: the child we were, the adult we are, the elder we might become. Perhaps the most beautiful time travel happens not through exotic physics, but through imagination and empathy. When we read letters from the past, we visit other times. When we plant trees for future generations, we send gifts into tomorrow. When we remember someone we've lost, we bring them briefly back into the present. When we dream, we slip sideways through time, mixing memory with possibility in combinations that would make quantum physicists envious. The universe may forbid us from physically visiting yesterday, but it has given us something perhaps more precious: the ability to carry yesterday with us wherever we go. Every photograph is a time machine, every story a portal to another when, every song a bridge across the years. We don't need exotic matter or cosmic strings to experience time travel. We need only the patience to remember and the courage to imagine. And maybe that's the real secret hidden in all those equations and paradoxes. Time travel was never about the technology. It was about recognizing that we are already miraculous temporal beings, conscious patterns of matter and energy that move through space-time, carrying meaning, memory, and hope. We are the universe's time machines, brief arrangements of atoms that experience the passage of time as something beautiful rather than just physical. The impossibility of visiting yesterday preserves the preciousness of today. The certainty that we'll all travel into the future together, 1 second at a time, creates the shared experience that makes love and loss and wonder possible. We are all time travelers on the same journey, companions moving through the mystery of existence at exactly the pace the cosmos intended. Perhaps that's miracle enough. And so, we arrive at the end of our temporal journey, though in a sense, we never really left the present moment. We've wandered through bent space-time and theoretical wormholes, puzzled over paradoxes, and marveled at the time travel happening all around us. We've seen that while the universe may allow us to slip forward through time, it seems remarkably protective of its past. Perhaps that's for the best. Maybe the beauty of time isn't in conquering it, but in surrendering to it, in accepting that each moment arrives once, unfolds gently, and then becomes memory. That the present is the only time machine we truly need. Tonight, as you drift towards sleep, you'll be traveling forward through time at exactly the pace the universe intended. And in your dreams, you might visit anyone you choose, childhood summers, imagined futures, or places that exist only in the gentle space between sleeping and waking. If you found any peace in this quiet expedition through time's mysteries, if the wonders of physics helped you settle into rest, we'd be honored if you follow us for more gentle journeys through science in the future. After all, tomorrow is just another destination in our shared voyage through time. Thanks for joining us here at Sleep Science. Sleep well, time traveler.